This is Mr. Martin. These are the video notes for section 9.3 for Geometry Honors. We're going to be looking at altitude on hypotenuse theorems. So we're looking at a right triangle, and we're going to draw the altitude to the hypotenuse. So I've got the altitude here drawn to the hypotenuse. And when we do this, we form a bunch of geometric means. Remember, geometric mean and mean proportional are the same thing. So before we get into that, it's important for you to remember and realize that a geometric mean, the means, the second and third terms, are the same. So we're going to get 3 geometric means from this theorem. Now, the 3 pieces of this triangle that are going to be the means are going to be the legs. So this leg can be a mean, the length of that leg. This leg, the length of this leg can be a mean. And then the altitude also is going to be a mean. Okay, so I'm going to go ahead and label this triangle A, B, C, and D. And these 3 purple highlighted segments are going to be the mean. So the first part of this theorem says that if the altitude is drawn to the hypotenuse of a right triangle, then the altitude is a geometric mean. So my altitude is CD. So here's my proportion, CD is a mean between the 2 parts of the hypotenuse. So the altitude drops down and it divides the hypotenuse AB into 2 pieces, AD and DB. So in this theorem, when we talk about the parts of the hypotenuse, we're talking about the 2 parts that the altitude divides it into. So the altitude is a mean between AD, that's the part to the left, and DB. Okay? So altitude is drawn to the hypotenuse of a right triangle. Then the altitude, CD, is a geometric mean between the 2 parts of the hypotenuse. So that's the first part. The second part, each leg is a geometric mean. So let's start with that. So I know I'm going to have 2 more proportions because there's 2 legs. And one of the legs is AC. So AC is a leg, and it's going to be a geometric mean. And BC is the other leg, so that's going to be a geometric mean. So I know that's going to go in the second and third spots. And it's a mean between the piece of the hypotenuse it is adjacent to. So if we go back up here, AC is next to this part of the hypotenuse. So that's going to be between AC or AD and the entire hypotenuse, which is AB. Alright, so we look on the other side, BC is going to be a mean between the part of the hypotenuse that it's next to, so BD, and also the entire hypotenuse, AB. Alright, so sometimes you may see these multiplied out using our means extremes products theorem. So if you like that, you can use it. I typically don't, but you can. So this would be CD squared is equal to AD times DB. And then these two, we would have the legs squared is equal to the part of the hypotenuse it's next to times the whole hypotenuse. And this one over here again would be the legs squared, BC squared, is equal to the part of the hypotenuse it's next to, BD, times the entire hypotenuse. So feel free to use whichever versions of those you like. Alright, so for the first example, we want to write the 3 geometric means given the altitude drawn to the hypotenuse of the right triangle. So we've got a right triangle. Right triangle, and we've got an altitude here. So again, I like to recognize which parts of this are going to be the mean. So I know the 2 legs, so that's one leg, which I just have labeled Y to make it a little bit easier. And this leg, which I've labeled X, and then the altitude, which I've labeled H. Sometimes we'll use H for height. So I know that those 3 pieces are going to be the mean. So I like to start with that. So I know that Y is going to be a geometric mean. and I know that h is going to be a geometric mean, and I know that the other leg, x, is going to be a geometric mean. So the legs are the mean between the part of the hypotenuse that they're adjacent to. For y, it would be a, and the entire hypotenuse, c. The altitude is a geometric mean between the two pieces of the hypotenuse. In this case, it's a and b. And here's my other leg. It's going to be a geometric mean between the part of the hypotenuse it's next to, b, and again the entire hypotenuse, c. So there's our three geometric means. Now let's go ahead and use this as an example to solve for some missing parts. So we can see here that we want to solve for the three pieces that would normally be the geometric means. I've got one leg, the second leg, and the altitude. These are going to be my geometric means. So I know that x is going to be a geometric mean, y is going to be a geometric mean, and z is going to be a geometric mean. Okay, so x is going to be between 3, the piece of the hypotenuse it's adjacent to, and the entire hypotenuse, which is going to be 12, 9 plus 3. So if I cross multiply, I get x squared is equal to 36, and then x is equal to 6. Now, normally with the algebra, we would have positive and negative, but since now we're talking about the length of a segment in a triangle, we only need the positive one. We basically are rejecting the negative one. Alright, moving on, the altitude is going to be the geometric mean between the two pieces of the hypotenuse, so that's 3 and 12. Go ahead and cross multiply. We get y squared is equal to, this should be a 9, sorry about that, 3 and 9. So that's 27. Again, we take the square root. We only need the positive one. Y is equal to the square root of 27. Make sure you write this in simplified radical form. So that's square root of 9 times the square root of 3, which is 3 root 3. And then z is going to be between the part of the hypotenuse it's next to, 9, and the entire hypotenuse, which is 12. Again, cross multiplying using our means extremes products theorem, I get that z squared is equal to 108. So z is equal to the square root of 108, which is the square root of 36 times the square root of 3, or 6 root 3. Right, as always, make sure you write down your questions and ask me when you see me in class. Moving on to the last example, we want to solve for p. So again, identifying the part of the picture that can be the mean, the geometric mean would be 10. So I know that 10 is going to be between the part of the hypotenuse it's adjacent to, p, and the entire hypotenuse, which in this case is p plus 21. So when I cross multiply, I get p times p plus 21 is equal to 100. I'm going to distribute to get p squared is equal to 21p, or plus 21p is equal to 100. Now I need to solve this, so I'm going to bring everything over to one side. So I get p squared plus 21p minus 100 is equal to 0. I'm going to see if this factors. So I need two factors of 100 that when added or subtracted equal 21. So 25 and 4 is going to work. So I know it's going to be a p over there and a p over there. It's got to equal 0. So 25 and 4. Since it's plus 21, I'm going to make that plus 25, make that minus 4. I'm going to use my zero product property. P plus 25 is going to be 0, or p minus 4 is going to be 0. Solve each of these. I get p is equal to negative 25. We're not going to use that one because we can't have a negative value here for p. Here I get p is equal to 4, and there's my final answer. So again, if you had any questions, make sure you write them down. Very important concept. We're going to be using it all the time throughout the chapter, and actually throughout a lot of the rest of the semester. So make sure you have a good understanding of how to write these um, proportions from this theorem. See you next time.